Okay, so the plan for today is to talk about undetermined coefficients. All right. So sections 3.5 and 3.6 concern two different methods for solving homogeneous differential equation, or sorry, non-homogeneous differential equations. So if we have a second order linear equation that looks like so, up until this point, we have looked at versions of this equation that have a zero right-hand side. All right, we are now going to be looking at equations where g is some non-zero function. All right, just to clear up some vocabulary in case I accidentally use this vocabulary in the future, what we would say about g is that it is not identically equal to zero. It's allowed to take on the value zero, it's just not allowed to be zero all the time if we're talking about a non-homogeneous equation. Okay, so there are two general classes of non-homogeneous equations that we're going to be dealing with, and they can be more or less broken up into easy and hard. Okay, and the easy ones are going to be dealt with by the method of this section, and the more difficult ones are going to be dealt with in section 3.6 when we're talking about variation of parameters. Now, I don't say easy and hard as a way to say that like it's not a measure of difficulty so much. It's a measure of the representability of the right hand side. If the right hand side is in a convenient form, then we can use the method of undetermined coefficients. If it's in an inconvenient form, then we have to use a different, more general technique. So that's the story here. Okay. Now, the way that we're going to approach this in general before we hone in on specifically the technique of undetermined coefficients is by following this general procedure. Okay. The first thing that we're always going to do is find the homogeneous solution. Okay, it's always step one. Okay. Second thing we're going to do is we're going to make a judgment based on the form of g of t. Okay. If it's easily representable, we'll use undetermined coefficients. Otherwise, we'll use what's called variation of parameters, which is the name of our other technique. Our solution is going to be the sum of y sub h of t and y sub p of t. This is the homogeneous solution. And this is the particular solution. And the particular solution is the one that comes from the non-homogeneous part. Okay, the last step is solve the initial value problem if necessary. All right, all make sense? Okay. So for undetermined coefficients, find an example here. We take some problem here. Y double prime minus 2y prime minus 3y equals 3e to the 2t. Okay. So our first step is to just deal with the homogeneous case. So we assume that the right-hand side is 0. We write down the characteristic equation. This happens to be an easy one. So we can find the roots of the characteristic equation are 3 and -1. That tells us that the homogeneous solution is equal to C1e to the 3t plus C2e to the minus t. That makes sense? Okay. Now, we've done the first part of the problem. Now what we need to do is deal with the non-homogeneous part. Okay. And in the honored tradition of solving differential equations, we're going to guess and then see if it works. Okay. So the undetermined coefficients here is a reference to the fact that we are going to guess that the particular solution, which you can either write as y sub p, or it's often written with a capital Y, whichever one is fine. We're going to guess that the particular solution has the form capital A times e to the 2t. where the e to the 2t part comes from this element here, and we're going to need to figure out what the coefficient a needs to be in order to make this work. So that is how we proceed. What you do is you plug in your guess for the particular solution into the differential equation and figure out what a has to be in order for this equation to make sense. So we differentiate twice here. We differentiate once here. And this we just distribute. Make sense? So we're left with negative 3a e to the 2t equals 3e to the 2t. So what do we know about a? Has to be negative 1. Okay? So what you would do, of course, is plug this into the equation here to see if it gives you the answer. Okay? If we plug it in, we're going to get 4e to the 2t for this, right? And then negative 2 times negative 2 e to the 4t minus 3, right? Or sorry. let's just write it out so we're not making silly mistakes. It's not a minus 2. Okay, written out, it's easier to see what's going on. I take 2 derivatives, I get a factor of negative 4 out front. I take 1 derivative, I get a factor of positive 4. And then here we get positive 3. So it will work. Okay, and that is to say that the overall solution to the differential equation, the general solution to the non-homogeneous equation, is c1 e to the 3t plus c2 e to the negative t minus e to the 2t. Make sense? Okay. Now, the reason why I was able to check just this part to see if my particular solution was correct is because what happens if I plug this into the original differential equation? I get 0 because it's the solution of the homogeneous part, right? So if you want to verify your particular solutions, you can do those separate from the whole, from the rest of the expression. You don't have to plug in the homogeneous part as well. Okay. Now that property, the fact that I get 0 if I plug this in, and I get the right-hand side if I plug that in, comes from linearity. If we didn't have a linear second-order equation, that wouldn't work. Okay, so this is a consequence of us talking about a very, very specific and well-behaved class of differential equations. All right. Let's look at this example. Okay, what's step one? We solve the homogeneous equation. If you're comfortable with this, you can skip steps and just write down the characteristic equation immediately. We've been really nice so far. Both of these have factored. The homogeneous solution is C1 e to the 2t plus C2 e to the minus t. Okay. Now, what should my guess be for the particular solution? To make a guess, right? My guess last time just kind of looked like the thing, except with a letter instead of a coefficient, right? Or a letter as the coefficient, representing the undetermined value. I don't want to use a in both places. They need to be different coefficients. Yeah, you just pick a different letter. Okay, so let's try this. So we're going to take this, plug it into this side of the differential equation, and then try to get things to match. So if we do this, we get AT plus BT squared double prime minus our guess prime minus 2 times our guess. This has to be equal to negative 2t plus 4t squared. All right, so what's the second derivative of a times t? That's 0, right? Because the derivative of t is 1, and the derivative of constant 0. Okay? What's the derivative of t squared? Second derivative of t squared? 2b. Okay? We take one derivative here. Derivative of a times t is, and the derivative of bt squared is, okay? And make sure that's in parentheses so you don't forget to distribute the minus sign. And there's no derivatives to take here. We just need to distribute. Is this okay? So when we are making a statement about whether or not two expressions are equivalent, okay, in this case polynomials, one of the ways that you can think about that equivalency is they're equal if and only if their coefficients match, okay? So what you want to do is we want to think about this is being written like so. I have a coefficient for the constant term. You can either think about this as 1 or t to the 0 power, whatever, right? You have the stuff times t, and then the stuff times t squared. And that has to be equal to this, whatever goes in there, okay? Now, collecting things, I have negative a plus 2b for the constant part. I have negative 2a minus 2b for the t part. And for the t squared part, I have negative 2b. You all agree with that? Okay. I have a problem. This has to match this, right? This has to match this. I don't have anything for this to match. I could say 0, but then I would have a system of 3 equations and 2 unknowns, which is overdetermined and unsolvable. Okay? The problem is up here. My guess isn't good enough. I need a third coefficient that I'm trying to find because this is a second order polynomial and it has 3 coefficients. 0 is the third one, right? Which means that when I'm looking for undetermined coefficients to represent that function, I have to include a third unknown in my guess. Okay? And this is the tricky part of this section, is when you are making your guesses must be complete in some sense. All right? And we'll talk about what that means through other examples. But this is, you would discover this mistake at this point in the problem. You wouldn't be able to find an A and B that work. Okay? And when that happens, it means there's an arithmetic or algebra mistake somewhere, or your guess wasn't good enough. Okay? So, we're going to have to start over. Okay? I'm just going to erase. You can copy down below. Why isn't that deleting? All right. So, I'm in the habit of writing my polynomials in descending order of power, so I'm going to write the thing like this. Technically, that changes what A and B means. I was just going off of what people said because I knew we were going to have to do it again. But it doesn't matter what the A, B, and C are, just as long as you keep it straight when you're doing your own work. Okay. So now we write all this out again. It's mostly just recopying. We already know that these things are easy to differentiate because they're polynomials. So we're not terribly upset about that. I did not leave myself enough room. Okay. So 2 derivatives is going to give us 2a t squared for this. Sorry, that's a mistake. Sorry, just 2a, right? Minus, take 1 derivative, we get 2at plus b. And then negative 2 times just this expression, so we'll go ahead and distribute. Negative 2at squared minus 2bt minus 2c, and that's going to be equal to our right-hand side. Now, we go through the same process that we mentioned before with collecting terms. Negative 2a times t squared plus all the stuff that has t's in it, so we're going to have negative 2a minus 2b times t, and then lastly 2a minus 2c. Okay. Yes, you're correct. Thank you. All right. Talking and writing and thinking at the same time is too much. Anyway. Okay. So now we have this set up. And what we want to do is through the matching of coefficients, write down a system of 3 equations and 3 unknowns. Negative 2a equal to 4. Negative 2a minus 2b is equal to negative 2. And 2a minus b minus 2c is equal to 0. This happens to be a terribly convenient system of equations because we can immediately go to back substitution, right? A is equal to negative 2. B is equal to negative 2 plus 2 times negative 2. All over negative 2. So we're going to get, what am I doing? Just 3 here, right? Okay, and then for C, negative 1/2 times B minus 2 times negative 2. So we get negative 1 1/2. Do your own work and check me. We agree? Okay. Oh, that's right. Yep, you're right. Okay. So this is why you check. I told you. Today's not a good day. All right. So now we're on the same page. Okay. All right. Sometimes I make mistakes on purpose. That was not one of them. That was just me not being able to read my own writing. Okay. Anyway, that's why we check. So put all this together. We have our expression now for our particular solution. So we may write the general solution to the non-homogeneous equation as C1e to the 2t plus C2e to the minus t minus 2t squared plus 3t minus 7/2. All agree? Okay. So in general, this is how these things proceed. All right. We will solve a homogeneous equation. We'll look at our right-hand side. We need to make sure that our guess for the right-hand side is good. All right. And then we work out as necessary, plug our guess in, and then we'll end up with a system of equations that we need to solve in order to determine the undetermined coefficients. Okay, and then once we have those undetermined coefficients, we can put everything back together. All right, so when we set things up, one of the things that we need to do is make sure that our guess is complete. All right, in the previous example, what we saw was our function had this form, okay? And the guess that we needed in order to make this work was a guess that looked like this, okay? Now, if I had a different right-hand side, say one that looked like this, what do you imagine the guess would have to look like in order for this to work? In order for us to check our guesses, what do we have to do? What is this? What are we doing? We're plugging it in, right? What happens if I plug sine into something where I have to take its derivative? I get cosines, right? Is this kind of guess going to be good enough? No, because I'm going to have cosines that I'm going to have to deal with, right? So we need the cosines. And yes, of course, when you take the derivatives, you're going to have the chain rule of the 2's popping out of these expressions or whatever, but those 2's get absorbed by the coefficient, right? So that part's okay. If your guess looked something like this, or sorry, if the right-hand side looks something like this, what do you imagine the guess would look like? Sorry, say that again. Not quite. That's we will get the product rule when we plug it in, right? But if I were to differentiate this using the product rule, I take the derivative of the first function, leave the second function alone, right? So I would end up with something that looks kind of like this because I would just get a 3 out in front. Okay. Then you take the derivative of the second function, leave the first function alone. What is that going to give me? Sine times an exponential, right? So it's the same kind of thing. And of course, you can write it as a times e to the 3t cosine plus b e to the 3t times sine. That's fine. I just prefer to write it this way. Okay, so what is the lesson we have learned about these things? What makes me have to add things to guesses? Derivatives, right? So when earlier we were talking about functions being easy to represent or hard to represent, the delineation there is whether or not its derivatives form cycles. If I differentiate a polynomial, I'm eventually going to get to 0, right? If I differentiate sine and cosine, I'm going to get a pattern of sine and cosines. If I differentiate exponential functions, I just get the exponential function back. Okay? So if the derivatives have some kind of distinct cyclical pattern to them, okay, then they are appropriate right-hand sides for us to use the method of undetermined coefficients on. If they don't, they're things like logarithms or tangents or something where the right-hand side doesn't work back to being the same class of functions, I can't construct a guess that will handle all of the possible derivatives that I might encounter. Okay, so the answer here is a cycle of derivatives. Right. Now, you don't need to think about it in terms of that sense. You just get a feeling for what kinds of things you need to guess, right? If it's a polynomial, you guess a polynomial that has all the terms in it. If you're got something that has sine, you make sure that you have the equivalent cosine thing too. Okay. All right. Questions about this part? Make sense? Okay. The other weirder problem that we can have is when the right-hand side is linearly dependent upon the homogeneous solution. So we did this example here, okay, and our homogeneous solutions were e to the 2t and e to the minus t. So if we look at that kind of example, except I have the right-hand side be this, 3e to the negative t. If I were to make a guess for the homogeneous solution, that was ae to the minus t. If I take this expression and I plug it into the differential equation, what am I going to get? Two derivatives, one derivative, no derivatives. What is this? It's 0, because this looks like part of the homogeneous solution, right? C2 e to the minus t. Okay, so I don't get, when I plug it in, my non-homogeneous right-hand side. So I'm going to have to guess something else. Obviously, the same sort of thing would happen if the right-hand side looked like the other member of my fundamental family of solutions. Okay, so the question becomes, what do we do here? Right? Right? So we're going to have to figure out some way to adjust this guess so that it can compensate for this strange problem that we have. Okay. Now, if we look at our original equation and we remember that its characteristic equation had the following form, maybe what we can do is take advantage of the technique that we talked about a couple of sections ago, right? Do you remember when we were dealing with the problem of repeated roots? And it was necessary for us to figure out a different solution that our characteristic equation in cases like this didn't cough up a second one. Okay? We're going to appeal to the same technique. All right? So our right-hand side is one that's dependent upon this solution here. Okay? So let us set up a similar problem, except I'm going to change the R to a D here to represent derivative. We're going to search for a function y here, and we're going to solve the non-homogeneous equation with the non-homogeneous, or with our right-hand side here. Okay. So what this is going to look like is y prime plus y is equal to 3e to the minus t. Okay. If we apply an integrating factor, our function is just 1, right? That's the function coefficient there. Okay. So what this tells us is that our integrating factor is just e to the t. So if we use the integrating factor, we're going to get e to the ty. We have a derivative of that expression. That's going to be equal to 3. Okay? Integrate both sides. Three t plus a constant. And then we differentiate by, or we divide by e to the t, and we're going to get 3t e to the minus t plus c e to the minus t. This right here gives us the hint that we need in order to be able to deal with whatever's going on. Okay? This is the element that we're going to have to use for our guess that we didn't know about beforehand. Okay? So, when we set up for this, instead of guessing this kind of thing, we're going to be guessing this kind of thing. And I don't need to have the e to the t part because I know that any number times e to the t is just going to give me 0. Right? So I can just skip that part of the guessing. So let's try this again. Our guess is going to look like a t e to the minus t. Our differential equation is y double prime minus y prime minus 2y equals, it was, 3e to the minus t. Double check, make sure that's right. Yeah. Okay, so now we plug all this in. Derivative of the first function, leave the second function alone. Plus the derivative of the second function, leave the first function alone. That still needs to be differentiated again. This is the same expression. And this one just gets copied. Okay, now we differentiate again. We get minus a e to the minus t minus the quantity. Repeat it again for the derivative. All right, so tedious. It's a lot of copying, but it's not hard. Okay, so we have all this set up now. And we want to collect terms at this point, right? Okay, so I have -2, -3, factors of that, right? Okay, and then I have +1, +1, -2 factors of that. So those all add out, which we're happy to see because I don't have any of those over on the right-hand side. Okay, so this reduces to -3a e to the minus t is equal to 3e to the minus t. A is -1. That is to say that our general solution for the differential equation is c1 e to the 2t plus c2 e to the -t minus t e to the -t. That make sense? Okay, two more things for us to cover in this section. What's the particular solution of this problem? Or sorry, what's the general solution to this problem? We'll say it that way. What is it? It's not a trick question. I'm just asking. Okay, so we talked earlier about how if we plugged in the homogeneous part of our solution into this differential equation, we're going to get 0, right? And if we plug in the particular solution to the differential equation, we get the right-hand side. Well, we just figured out what the particular solution is for this. So if I plug this expression into the differential equation, I get that part of the right-hand side. I should also, if I plug in this, get that out of this differential equation, because it's the same differential equation. Okay? So this means two things for us. Number one, I can just write down what the answer is. It's hard to remember. Yeah. I can use that old answer that I've already done, right? So if I've already done the work, then I can just use my old answers. And if I have a complicated problem presented to me and I haven't done the problems individually, I can break up the particular, or I can break up the right-hand side into sensible pieces and do those problems individually. So if my right-hand side, for instance, looked like this, I could do this problem and then do this problem and then add the answers together. I don't have to do them all at once. Okay? So, and this again is a consequence of linearity. It wouldn't work if we didn't have a linear equation. All right. Make sense? Okay. All right. So we have this as our equation here. If I write down the characteristic equation, I can see that this is a perfect square trinomial. And so what I get for my roots are 5 repeated, which is to say that the homogeneous solution is equal to C1 e to the negative 5t plus C2t e to the negative 5t, using our formulas from those previous sections. Sorry, you're okay. There. That's what I meant to write. Sorry, those should both be plus signs. All right, sorry. Now that I have correctly written down the question, we have a problem. What's our problem? right-hand side is linearly dependent upon the homogeneous solution, right? And it's not like the case that we talked about before, right? Before, the linear dependence was no t, right? And all I did was I showed you that eventually we could figure out that we just needed to add a t in order for the guess to work, right? Okay. If we were to go through the steps to figure this out, we would need to, as we did in the previous case, employ reduction of order and determine what a proper guess would look like. Okay? Now, turns out that trying the dumb thing works. You just add a power of t. Okay? Now, you can justify this, of course, by doing reduction of order, but the thing that you do in these cases is you just add a power of t, and it's fine. So we go through the same process. We have some product rules to do. Okay, we can see how the computations are going to work out, right? You're going to get the same thing. All of those terms are going to add out serendipitously, and you're just going to be left with stuff that looks like this in order to figure out what the coefficient is. Okay. The point is that our guesses need that extra power of 2 in order to work. Okay. Make sense? All right. So the next element to this are initial value problems. Okay. And initial value problems work the way that you would think that they do. It's just that you can't forget to put in the particular solution as part of your function y. So if you're given your initial value problem for one of these things, so we'll just go with the example that we had before. I have no idea what this is going to look like. I'm just making up the initial values here. It'll be fine. Okay. So this is our differential equation. We've got everything set up here. We know that at 0, our solution has to have the value. I'm going to copy down our answer here so we're not trying to remember what it was. All right, so that's what this thing looks like. We're trying to find C1 and C2. Plug in 0 equal to 1, and then we're going to get C1 e to the 0, so that's just C1, plus C2 e to the 0, so that's just 1, plus 0 because of this t, plus a 0 because of that t squared, plus a 0 because of that t, minus 7 halves. Okay, so the initial condition, or sorry, the particular solution factors into the computation here. In order to do the second initial value, we need to, of course, differentiate this expression. We're going to get 2c1 e to the 2t minus c2 e to the minus t minus e to the minus t plus te to the minus t minus 4t plus 3 plus a 0. And then double check my calculus because I've already messed up a couple times today. Yeah, so I was being tricky there. Okay, so there's a minus sign here. When you differentiate e to the minus c, you get a minus sign. So there's two minus signs. That's why it's plus. But thank you for double checking. Yeah. Oh, well, copy mistakes happen too. Anyway, so we have this expression. We can now plug in our 0 for y prime. That's supposed to be equal to 2. 2 times c1 e to the 0 minus c2 e to the 0 minus e to the 0. So that's minus 1 plus 0 plus 0 plus 3. That makes sense. This gives us a system of two equations and two unknowns. We're going to have c1 plus c2 is equal to 9 halves. And 2c1 minus c2 is going to be equal to 0. Agree with all that. Okay. So we add our two equations together. 3c1 is going to be equal to 9 halves. So c1 is equal to 3 halves. And the c2 must then be equal to 3. That's what it says. We'll see if it looks right. Okay, so we'll use Desmos to double check ourselves here. First thing that we do is we're going to create a tangent line. Our derivative is 2. We pass through our point 0, and our function was equal to 1, right? Just as a note about Desmos, when you're using it for this kind of thing, if you set y equals, you have to use the variable x in order for it to plot lines and stuff. If I would have typed it as a function, I could have used t, but because I wrote it using y originally, it wants y's and x's. We'll type the other one as f of t though. All right, and so it is we'll set the values for c1 and c2 in a second. E to the 2t plus c2 e to the negative t minus t e to the negative t minus 2t squared plus 3t minus 7 halves. And then it gave us these slider values that we can play around with. C1 was 3/2, and this was 3. And if we zoom in, we can see that our solution is indeed obeying that tangent line that represents our initial condition. Okay, so we did it. All right, our particular solution is correct. We applied the initial values appropriately, did everything right. Okay, just it's an easy trap to fall into when you're working these problems out, to forget to use the particular solution as part of finding C1 and C2, so don't forget to do that. Okay, so next up, we are going to be looking at section 3.6, which is variation of parameters, which is how we solve other types of problems. Okay, variation of parameters is a general technique. It will always work, but it is more work than undetermined coefficients if undetermined coefficients will apply to a particular problem. Okay, I will say, if this is something that you're a little bit sketchy on or worried about, to think about between now and next class, variation of parameters does require integrating. Okay, it is an integration technique, and we're going to see integrals involving stuff that you don't like to see integrals of sometimes, like tangents and trig functions and stuff like that. So that's where we're going to be going with that. And I will also say, as a last point, please don't make a big ruckus. The way that I teach the material for that section is not the way that it is covered in the textbook. I'm going to present a different but equivalent version of the ideas that I think are easier to remember. All right. So don't be gone next class, because what we're going to be talking about is not, it's in the online notes if you need to look through and follow along with what's going on, but I do not present that section in the way that it is presented in the textbook. Okay, anyway, so that's all for today. Take care, and we'll do this again on Wednesday.